Let's first take a very simple example whereby I have two point masses which I connected through a massless rod. A little bit artificial, but later I will relax this situation. I have here a mass m1 and I have here a mass m2, and I will assume that these masses themselves have no finite size. It's a point mass. So are these two discrete masses. And I rotate this system about an axis perpendicular to the line that connects them. And let this distance be r1, and let this distance be r2. And I want to know the moment of inertia about this axis. As we defined, moment of inertia is the sum of m of I over all the masses here. In this case, I equals 1 to 2, because we only have 2, for ri squared. And r is the distance from the mass elements to the axis of rotation. So that's relatively easy here. This is the distance from this mass to this axis, because it's already 90 degrees, and this is the distance from this mass to the axis. So in this particular case, we find that I, about this axis, equals m1 times r1 squared plus m2 times r2 squared. Now imagine that I rotate this system about this axis, again perpendicular to the direction that connects the two masses. Now I want to know what the moment of inertia is about this axis. Well, since m1 has no size, r1 is now 0. There is no distance between this mass and this axis of rotation. So the only mass that contributes to the moment of inertia is mass 2, and so we now find that the sum of m of I ri squared is now simply m2 times this distance, the distance from m2 to this axis, which is r1 plus r2 squared. And this number is different from this number. So the two are clearly not the same. So this shows you that moments of inertia do depend very much on which axis you choose. It's not an intrinsic property of, in this case, two masses. It depends on how you choose the axis. If I chose the axis to coincide with the massless rod that connects the two, then the moment of inertia would be 0. Because if here is that point mass m2, and here is the point mass m1, and here is the massless rod that connects them, clearly, if this is a point mass, the distance of this mass to this axis of rotation is 0, both for this one and for this one. So here you would have a moment of inertia which equals 0. So there is a huge difference about how you choose the axis. If I continue with this rather artificial situation, whereby we have point masses, m2, and we have a point mass m1. Point mass means no finite size, and this is a massless bar that connects the two. And if now I make them rotate about this axis at an angle theta, and this is r1, and this is r2. I now have to remember that I equals the sum, I equals 1 to 2 of mi times ri squared. But ri is the distance from the mass to the axis of rotation. That distance is this, 4(1), and this equals r1 times the sine of theta, and that distance here equals r2 times the sine of theta. So now the moment of inertia becomes m1 times R1 sine theta squared plus M2 times R2 sine theta squared. So I could write down that it is sine square theta times M1 R1 squared plus M2 R2 squared. And you can see immediately that when theta equals 90 degrees, that means when the axis is perpendicular to the line that connects them, then you have a maximum. We already derived that. But when theta equals 0, the axis is like this, then the moment of inertia equals 0. And here the moment of inertia is the maximum value possible. So it very much depends on the geometry.